All right. The next thing up is energetics. And like I said, there's the energetics of a solution mixture is where we get into the numbers of this. And that first part is the qualitative, or the big picture of the what and the why and the how these things are mixing. The next thing to talk about is the cost of it, the numbers, the accounting of this. Energetics are the cost of things mixing. Okay, so if we're going to talk about what causes the accounting of this, we need to break this down into the different pieces. I told you that in order for things to mix, you have to break apart the solvent. You have to break apart the solute. And you will get back energy by dropping them into each other when the intermolecular forces are allowed to pull the solvent and the solute together. So there are three different energetics or thermodynamic properties involved when you mix things. The first step is, well, break apart, say, the solution, the solute. That's an endothermic process. You have to put energy into it to break it apart. This breaking apart the solution is endothermic. The next part is breaking apart the solute. That will also cost energy. And the last thing is mixing them or bringing them together. That's where energy is released. Now, the net result of this is the heat of solution. The sum of those three parts is the heat of solution. The heat of solution is, in some books, also called the heat of solvation or heat of dissolution. All three of those things represent the sum of those other three parts. Now, mixing does occur because of entropy. But that heat of solution, the net result of taking salt crystals and throwing them in the water and forming a solution, this is the energy of the heat of solution. And it is the sum of three other pieces. The price you have to pay to break apart a solute, and that's an endothermic process, a price you pay to break apart the salt crystal. That delta H is going to be greater than zero because you have to give energy to the salt crystal to break it apart. To break apart the water, that's also going to be an endothermic process. You have to put energy into the solvent. The heat of solvent is step two, a second piece that you have to accomplish in order to form the solution. And the last thing is, when you combine these things, you get energy back. That's the heat of mixing, and that's exothermic. Bringing these pieces together to form the solution, that's exothermic. Now, the heat of solution, or the heat of mixing, is exothermic, and the heat of solution is the heat of solute, solvent, and mixing combined, added together. And there's a bunch of problems they can hit you with on this. They can give you any three of those and ask you for the fourth one. They can ask you to characterize any of these. They can ask you, heat of solvent, is it endothermic or exothermic? Heat of mixing, endothermic or exothermic? They can also give you those three numbers on the end and ask you that when the solution forms, does it absorb energy or release energy? And that's really just it could go either way. You have to add up the other three to find out whether the heat of solution is endothermic or exothermic. But does it make sense that the heat of solute is endothermic? To break apart that crystal, does it make sense? You got to put energy into that.
Yes.
And the solvent, breaking that apart. If somebody asks you heat of solvent, endothermic or exothermic, what are you going to tell
them? I would say it's endothermic.
You got it. Now, if I drop a plus into a minus, or a penny into a well, or a sodium chloride into a water and let the intermolecular forces pull them together, is that endothermic or exothermic? Do you have to pay a price to drop a penny in a well? If you take 2 minutes plus and minus. Does it cost any energy to let them snap together?
Not really, right?
No, you get that for free. Yeah. Penny, all you got to do is let it go. It's going to fall into the well. When these intermolecular forces are attractions, heat of mixing, all you got to do is bring these things that you paid energy to pull apart, bring them next to something else, bring the sodium ion next to the water and let go of it. And like dropping a penny into a well, they'll snap together. And when they hit, that's the collision, that's the splash, that's the energy that comes out of it. So mixing is an exothermic process. Now heat of solution, the sum of those, well, if I've got 2 indo and 1 exo, it could go either way. I could have, for example, the heat of solute is endothermic, heat of solvent is endothermic. I have to pay to break things apart. And then I get energy back when I drop them together. But that could go either way. If my heat of mixing is greater than the sum of my solvent and solute, in other words, if I get more money back than I paid to break apart the solvent and paid to break apart the solute, well, then the net process is profitable. Energy comes out. If I mix these things, I'll burn my fingers. In contrast, if the heat of mixing is less than the absolute value of the heat of solvent and solute, well, then it's gonna need some more energy to happen. And this process will still happen and it'll still be spontaneous because it doesn't matter that it's an uphill fight. It doesn't matter you have to put energy into it to make this happen, because the driving force is not the energy, it's the entropy, the shape of it. So as long as these two, as long as that heat of solution is small enough, it doesn't matter if it's endothermic or exothermic. It's still spontaneous because it's the entropy that's driving the bus. And so when you're looking at these different systems, questions they might ask you is, if they give you any 2 of these, what's the third? And what's the sum of them? Is it endothermic or exothermic? And you really got to add up the heat of mixing, which is negative, to the heat of solvent and solute, which are positive, to find out if the heat of solution or solvation is endothermic or exothermic. Now,
So
there's also,
question.
yeah, go for it.
So to calculate the heat, right? So we have to break down like how do you say, into
Usually,
ions, right? Molecules into ions, right?
if
Or
it's
no,
if
am I
it's
getting confused?
that's true. So the heat of solute, if it's like sodium chloride, the heat of solute is the price to separate the ions, to take the sodium ion away from the chloride ion, to separate it so that it can then mix. The heat of solute is always going to be endothermic. And you're right, for ionic materials, for electrolytes, that's the price it pays to pull these crystals apart. Now, there's also things like sugar crystals, which are stuck together with different ways. They don't break into ions. It's a molecular compound, but you're still taking one sugar molecule away from another. You always have to pay the price for the heat of solute. That's kind of an interesting question, too. Do you remember last semester we talked about lattice energy?
Oh, I don't remember. It's been a long time. I won't lie to you.
No worries. Here's what lattice energy is. Sodium chloride melts at like 3,000 degrees Fahrenheit. Sodium chloride, 3,000 degrees Fahrenheit. Iron melts at something like 1,600. It's harder to melt sodium chloride than it is to melt an iron bar. And if you look at the attraction, we did something called the Born-Haber cycle last semester, where we're looking at how by adding up, things like ionization energy and electron affinity, we could figure out what the cost would be to, or why these things stick together so strongly. And it turns out it doesn't explain it for sodium chloride. There's a piece missing. And the piece that we discovered last semester that's missing is that you're not dropping one sodium ion into one chloride ion. It's not two atoms snapping together. It's a sodium ion falling into a whole field of chloride ions, a whole lattice work. And that sodium ion is being pulled by millions of chloride atoms, moles of chloride atoms all around it. That's the lattice energy. When you form sodium chloride, the reason it is incredibly exothermic to form sodium chloride from like sodium metal and chlorine gas is because you accomplish this lattice work. So lattice energy is exothermic. Lattice energy is the energy that comes out when you drop these ions into each other and you form that complete lattice work. Do you see where lattice energy it exists in this equation?
On the mix?
No, because we're not forming a crystal there with the mix, right? We're just forming a solution, a mixture. We started with a crystal. We started with, I don't know, sodium chloride, right? If your solute is, like you said, an ionic material that you have to pull it apart, pull it into ions, the heat of solute is the price you have to pay to tear apart that lattice work. And lattice energy is the energy that comes out when you form the lattice work. So another way they'll make these problems a little bit confusing is, yeah, if they give you any three, you can get the fourth one. But maybe they don't give you three of them. Maybe they give you the heat of solvent, the heat of mixing, and the lattice energy, which is exothermic. The trick is the lattice energy, which is exothermic, is equal to but opposite the heat of solute. So sometimes they'll be a little bit tricky there. In fact, they do it not so often to be tricky, but more often just because we're a little bit lazy. It's the lattice energy. There's whole tables of lattice energy, the energy that comes out when you form a crystal. And it's exactly the same as the heat of solute for ionic materials. It's just equal to the opposite of it. So if they give you the lattice energy, and be careful about how they read it. Lattice energy is always exothermic, but sometimes they'll say, the lattice energy is 25 kilojoules. What they mean is it's negative 25 kilojoules, but they're just giving you the absolute value of it. And the absolute value of the lattice energy is for a crystal dissolving is going to be equal to the heat of solute. So remember that lattice energy is always negative, even if they don't give it to you in a negative form, if they just give you the magnitude. And the heat of solute is always positive. And heat of solvent is also positive. So if they give you the yeah, go for it.
So are we going to encounter problems with the lattice this semester?
Oh yeah, you will see them in the homework and the labs and in other things. Because like I said, this is the picture. This is the equation to find the heat of solution. But but you're going to have to dig for those three pieces on the right sometimes. The heat of solute may be buried, may be hidden by telling you the lattice energy instead, because it's easier to come by. Okay. So they won't always give you the three pieces on the right. Sometimes instead of heat of solute, especially for ionic materials, they'll give you lattice energy. You need to know that lattice energy and heat of solute are equal but opposite. So when you're given the lattice energy, just flip the sign or make it positive, and that's your heat of solute. And so it can be a little bit tricky there. For that matter, solvent and heat of mixing, they can play a trick with that one too. Because you're going to try and combine these things. But sometimes they give you heat of hydration instead. When we're mixing things, we so often mix things in water. And so the energy it takes to pull apart the water, is significant, and we use it over and over and over and over again. So in order to keep it simpler, when you're mixing things with water, we will sometimes not give you the heat of mixing, we will pre-add to the heat of mixing the heat of the cost that it takes to pull apart the water. And those two together, the heat of mixing and the heat of solution for water, is called the heat of hydration. And that makes it easier because now I just need to take my heat of solute, or the opposite of my lattice energy, and add to it the heat of hydration. Then I only have to add two things to find out whether my fingers get cold or hot when I mix these things. But so you can simplify this puzzle by not having to find the heat of solvent and the heat of mixing if they give you the heat of hydration. Those two steps, the 2 and the 3 combined, are the heat of hydration if you're using water. Then all you got to do is add to it the heat of solute, and you can get that third piece, whether it's endothermic or exothermic. So heat of hydration is it's kind of a trick, like the lattice work energy. But this is what I do. This is what I put on my paper when I'm looking at these things. If somebody says, okay, when you mix these things, did it get hot? Did it get cold? What are the energetics involved? I write these 4 things right across the top of the paper. The heat of solution, which is the sum, the heat of solute, solvent, and mixing, which are the solute and solvent are the price I pay to tear them apart. And the heat of mixing is exothermic. And then, like I said, you need to be able to spot that the solvent and mixing for water combine the heat of hydration. So they might not give you any of those. They might not give you the solute, the solvent, or the mixing. They might just give you the lattice energy and, well, the heat of hydration. And you need to know that the heat of hydration is just solvent and mixing combined for water. By the way, I wrote underneath it that the heat of hydration is negative, right? Does that make sense? I mean, heat of mixing is negative, it's exothermic. Heat of solvent is endothermic, positive. How did I know that the sum of those two was going to be negative? The heat of hydration is going to be exothermic. If mixing is negative and solvent is positive, couldn't it have gone either way? What's the trick? Why can you count on heat of hydration to be negative?
I can only assume that it takes more energy to break things apart.
Well, actually, this is saying that it'll take less. Yeah. The energy, because it doesn't take any energy at all to mix it. You just got to let it go. And so the energy comes out when you drop the penny in the well. That's the splash. But the splash is always going to be bigger than the energy it took to break apart the solvent. Because if it wasn't, the stuff wouldn't mix. Remember, the heat of solute is always a positive number, right? So if the solvent and mixing were positive numbers, then there would be this huge barrier. In other words, oil and water. That if the heat of mixing isn't enough to overcome at least the solvent, then there's no way it can overcome the solvent and the solute combined. And oil and water won't mix. You will not have a mixture. So the heat of solution doesn't matter because it's not possible to mix them.
So the heat of mix should be greater enough to break down the solvent so that you can make it happen.
Exactly. Because when you do the heat of mixing, the energy that comes out is the energy you're using to break apart the salt and the water. And it doesn't have to be, hugely over it. It could even lose a little bit. It just needs to be close. Because remember, it's the entropy that's causing it to happen. But if the heat of mixing isn't big enough, it won't be allowed to interact. You can't do the mixing because you got to go too far uphill. The driving force is still entropy. So it's possible that this net thing could be a loss. You might have to put energy into it. If you dissolve calcium chloride in water, for example, calcium carbonate in water, your fingers will get cold because the heat of mixing is close to, but not a huge amount more. And so you feel a chill when you mix them. But there's a bunch of problems in the homework where you will play with this, and they'll ask you, does it get hot? Does it get cold? they'll ask you questions like, what's the heat of solute? Or what's the heat of hydration? And you need to get comfortable and familiar with these terms so that you can navigate the process. You can see the connections. Like I said, when I'm uncertain, I write those 4 things right across the top of my page. Solution is solute plus solvent plus mixing. The first 2 are always a positive, and the last one's always a negative. And then I can go on a scavenger hunt. If they give me something like heat of hydration, I can say, oh, okay, I see where it is. It mixes these 2. Or if they give me lattice energy, I can say, okay, that's the opposite of the solute, and I can match them together. But I always start with those 4 across the top. And then I try and fill in the gaps.
Okay, those are good tips. Thank you.
You're welcome. All right, so that's about it for tonight.